Hi Falcons. Today what we're going to talk about is molecular shapes. Molecular shapes are determined by what's called the VSEPR theory, or valence shell electron pair repulsion theory. It's a big set of words, VSEPR, but really what it's talking about is the idea that the things that are around this central atom, whether they are bonded atoms or unshared pairs of electrons, repel one another. The atoms repel each other because they're surrounded by an electron cloud, which is negative. The unshared pairs of electrons repel one another because, again, they're negative and things of similar charge would repel. So then in order to determine the shape of a molecule, what you have to look at is how many things there are around that central atom. Those things could be bonded atoms or they could be unshared pairs of electrons, which you would determine when drawing a Lewis dot structure for that particular molecule. What I'm showing you here is a linear molecule. You can see it's kind of a straight line. We would measure this and say that this is 180 degrees around this central, the black central carbon atom. This molecule, for example, would be carbon, nitrogen, and hydrogen, and would be at 180 degrees. Looking here, that central atom has two bonded atoms and 0 unshared pairs of electrons, meaning that these two things would spread out to the greatest degree possible. The example I always give of this would be to imagine if you had two magnets that were repelling each other in each arm. Where would your arms go? Well, they would go straight across, trying to get as far away as they possibly could from one another. That's the same thing here. If I was this central atom, my two arms would be directly out to the sides, 180 degrees, the largest possible angle they could get away from one another. Next, what I'm going to talk about are two examples where there are three things around the central atom. The first one of these is called trigonal planar. In this example here, I have a carbon double bonded to an oxygen and then single bonded to two hydrogens. You can see that it forms a triangle shape, and it's flat, meaning if I was to set this down on the table, you can see that it's flat in shape, okay? And this angle here, if you were to measure it, any of these angles would be 120 degrees. Again, using that example of magnets, if you were to imagine I had a magnet in each hand repelling each other and one tied to my feet, my arms would go, instead of at 90, would go up slightly, trying to get the greatest distance between my arms and my feet. Same distance here, 120 degrees, 120 degrees, 120 degrees, adding up to 360, a full circle around. Again, three things around the central atom, all going for maximum repulsion. This one is showing you a similar idea. In this one, I have two things bonded to the atom, and in this case, nitrogen here would have one unshared pair that would be invisible, but would be coming off right here. So two unshared electrons right up here in the electron cloud of nitrogen. But again, that would be three things. 1, 2, 3. So this one actually has a similar angle, which if I was to show you these, kind of superimpose them on one another, you can see that they are at the same angle, 120 degrees. It's just that that one unshared pair of electrons that's sitting here is invisible to you in the shape of the molecule. This molecular shape would be called bent or 120 degree bent. The next three I'm going to show you all have four things around the central atom. Either two bonded atoms and two unshared pairs, three bonded atoms and one unshared pair, or four bonded atoms and no unshared pairs. The first one I'm going to show you is a water molecule. This one is, again, that bent shape, okay, but the bend is going to be slightly tighter because it has two unshared pairs of electrons coming off here. The four things around the central atom will come to something close to 109.5 degrees. Again, using my example of the magnets, if I had a magnet in both hands and one on both feet, you might say, well, then 90 degrees around would be the best angle. But in fact, if you think of it in 3 dimensions, if I was to spread my feet and have one magnet going forward, one back, and one to each side, I could increase that angle to greater than 90 when using 3 dimensions, which you can kind of see here on this central atom. You can see that you actually have one that's coming out. These ones are coming back slightly from you as the viewer. And all of these angles would be slightly greater than 90 degrees. It's 109.5 roughly. This one here has a central atom and 4 atoms bonded to it, and is called a tetrahedral. Tetra meaning 4. So 4 things around the central atom. This, for example, would be methane, a carbon and 4 hydrogens. But anytime you have a central atom with 4 bonded atoms, it's going to form this tetrahedral shape and be 109.5 degrees. Next, I'm going to show you what's called a trigonal pyramidal shape. Trigonal pyramidal has 3 bonded atoms, and then, if you can imagine again, an unshared pair of electrons here. Again, if you were to look at these two, you'd see that they're very similar in that shape. It's just that that last unshared pair of electrons is invisible to be seen. Now, interestingly, that unshared pair of electrons repels the other atoms slightly more than the atoms do to each other, which makes this angle reduce slightly, which is why I've written here less than 109.5. You don't have to remember the additional numbers, but it might be helpful to know that this guy repels a little bit more, so this angle would be a little bit more tight due to that extra repulsion. And then again, if I was to show you that water molecule, again, if you were to look at these and look at these angles, you'd see that they're very similar, okay? Because again, he's bent at that 109.5 degrees, actually slightly less than that because of those 2 unshared pairs of electrons. So I hope this was helpful, and this is molecular shapes. Thanks, Falcons.